All right, so last thing in this unit is efficiency. And while there's like a little bit of calculating, it's pretty straightforward stuff. What I'm most concerned with in terms of efficiency is that you understand what efficiency is. Okay? Not only is it a fairly large focus of our society these days, trying to be more efficient with our use of energy and use less and have less environmental impact and all of that. Okay? It's also important from a physics perspective to know what it is. Okay? Because it's always good to do something more efficiently. Okay? To make the maximum use of our resources as possible. Okay? And that's what efficiency is. Okay? Efficiency is a percentage. It's a measure of how much of the work that you put in did you actually get out. Right? So if I fill up my car with a tank of gas, and that tank of gas represents 10,000 joules worth of energy, okay, and my truck can only do 2,000 joules worth of work with 10,000 joules worth of energy, it's only how efficient. What's the percentage if I'm using 2,000 out of 10,000? 20%. Is that very good? No. I don't like the sound of 20%. Nobody likes the sound of 20%. Like, I'm not going to the doctor if they're only right 20% of the time. Right? Like, that's not good. Okay? I might as well cut out my own appendix with a grapefruit spoon. Okay? Like, I wouldn't want to, accept 20%. Except we do. We accept 20% efficiency all the time. Okay? Most gasoline-powered vehicles run at maybe around slightly more than that. Okay? In terms of the amount of energy that there is available versus how much of it they effectively use to do work. Okay? There's a lot of energy lost in energy conversions. So, anytime you convert energy from one form to another, there's going to be some that's lost. How much of it is lost is what affects your efficiency. Okay? No conversion of energy is 100% efficient. Okay? In the perfect physical world, sure they are. Okay? And that's what we've been dealing with up until now. And we always say, if I did 10 joules worth of work on that spring, the spring is going to do 10 joules worth of work on this, and it's going to do. In the real world, that doesn't happen. Okay? If I put 10 joules worth of work into drawing a bow back to shoot an arrow, I'd be lucky if that arrow gets 6.5, 7 joules. Okay? Because there's going to be some heat in performing the bow. There's going to be sound when I let go of the string. Okay? All of those represent places where energy can be lost. The more conversions of energy between my source of energy and my final work, the worse my efficiency will be. Because at every step, some energy is going to be lost. So what we want to do is try and reduce the amount of conversions or find more efficient conversions. Okay? That sort of makes sense to everybody? Okay, so one of the best places to see this, okay, is in the different types of vehicles that we have the choices to drive. Okay, so most of us, okay, probably drive a regular gasoline-powered vehicle. Okay, most of the cars on the road are still gasoline-powered only. Okay, so in a gasoline-powered vehicle, okay, a lot of the energy in your fuel is lost as heat. It just goes right out the window. Okay, in fact, you have systems in your car whose sole purpose is to take the heat that's wasted and get rid of it so that your car doesn't melt down. Okay, so you have a system on your engine called the cooling system that consists of your water pump, the coolant, and your radiator. It circulates the coolant through the engine block, keeping the engine block from getting so hot that it would melt. Okay, so there's energy that's actually taken in order to get rid of the excess heat that's produced by your motor. Right? That's not very efficient. The conversion of heat to mechanical energy, which we talked about like the second day of this unit, is not a very efficient conversion. So in your engine, okay, you're going to lose 68 to 72% of the energy in your fuel. Lost. It's not doing any work. It's just gone. Okay, so that could be the exhaust. I mean, have you ever noticed, if you've never noticed this, but the gas that comes out of the tailpipe is hot. Okay, and that represents a lot of wasted energy. And that energy comes out, it's hot, and it's just going out the back. It's not doing anything. Okay, so 58 to 62% of the energy in your fuel is lost as heat out the tailpipe. okay? Combustion losses, so inefficiency in the combustion, the fuel doesn't burn completely, okay? Represents another 3% of the energy in the fuel lost, okay? Pumping, so that would be your water pump, things like that, okay? 4% of the energy in your fuel is used to power the water pump, okay? Friction, internal friction, okay? I mean, we put oil in our car, it's really important, okay? If your car doesn't have oil in it, it will die a terrible death, okay? But there's still going to be some friction between the moving parts of your car, and that represents 3% of the energy in your fuel, okay? We haven't moved forward yet, we've just turned the car on. This is what the car does without you driving it. Okay, it loses 68 to 72% of the energy in your fuel. So let's put it in real terms. I put $100 worth of gas in my truck. $72 of that goes up in smoke. That makes you want to cry when you're at the pump and your truck is going chug-a-lug, 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 because it's just, yeah, it's sad. Okay, electrical losses. Your car has lots of electrical devices in it, okay? And to power those electrical devices is a part called the alternator. Okay? The alternator is a spinning thing that has a belt that comes off the drive shaft that spins it and generates electricity to power all the electrical devices in your car. That takes energy from the engine. That's no longer powering you forward. It's doing something useful, but it's not powering your car forward. Okay, so that would be climate control, fans, seat and steering wheel warmers. So the more fancy stuff you have in your car, the bigger that number gets. So if you've got the seat warmers, and you've got the rear window defogger, and you've got the power door locks, and the power windows, and the massaging seats, because there's cars that have that now. Okay, so if you got like, that model, there's going to be more electrical losses in all of that, the touch screen, okay, all of that stuff. Okay. Parasitic losses, that's just stuff that bleeds away, okay, just that's lost. Water, fuel, oil pumps, ignition systems, engine control systems, all those things just have a little bit of energy that they're taking from the car, okay, that's not driving the car forward. So that means energy to the wheels, 16 to 25%. So of that $100 worth of fuel, somewhere between $16 and $25 of it is actually doing what my car is supposed to do. Go forward. Or backward if I'm in reverse. Okay? Is that pretty inefficient? And the bigger your car, the less efficient it's going to be. Okay? The bigger the motor, the less efficient your car is going to be. Okay? All right. Drivetrain losses are over here, 3 to 5%. Idle losses, 3%. Okay? So that would be when you're stuck in traffic. Most modern cars now have that auto shut off. So when you pull up to a light, the engine actually shuts off while you're waiting for the light. Okay, I find that incredibly annoying. I always disable it. If I'm in a rental, I disable it. Okay, but yeah, that's another one. But it limits the amount of idle losses. It saves me $3 on the $100 tank of gas. So maybe I shouldn't shut it off. Now, how many people have a hybrid car? Okay, we recently bought a plug-in hybrid vehicle because my wife works downtown and they have plug-ins that are free. And I'm like, oh, we ain't no dummy. We're going to plug in and we're going to get free gas because I'm tired of watching all those other people who have electric cars get free gas. So I'm going to get free gas. I'm going to be part of the problem. We got nasty notes on our car. Oh yeah. Yeah. People like even know, dude, why should you play your car on my dime? Take it up with town council. I didn't make this decision. Don't hate the player. Hate the game. Okay. All right, so if you're in a plug-in hybrid or any type of hybrid car, okay, you have the opportunity to be more efficient because electric engines are more efficient than gas engines. They're not converting thermal energy into mechanical energy as much. Okay, they still have a gas motor, okay, and that gas motor does help the car forward, right? But it doesn't have to run all the time. And it normally doesn't have to work as hard because in a hybrid vehicle, when it's under load, so when you press down on the gas to accelerate, that's when the electric motor kicks in. And the electric motor assists the gas motor so it doesn't work as hard and doesn't burn as much fuel. Okay? If you're just cruising down the road on the highway, your electric motor very rarely kicks in. You're basically just running on gas at that point because it's not very hard work. That's when your car is most efficient anyway. If you start going up a hill, the electric motor will kick in and help the gas motor a little bit. Okay? But hybrid vehicles are generally going to be the most productive or most efficient in stop and go traffic when you would be using the most gas. And cruising along the highway doesn't use nearly as much gas. Okay, so if we're looking at a comparison here, engine losses, it's about the same. It's still a gas engine. When it's running, it's a gas engine. It does what that gas engine does. Okay, so there's going to be radiator, exhaust, heat, combustion pumping, all that stuff. 65 to 69%. Again, it doesn't have to work quite as hard, so it's a little bit better. Okay, parasitic losses, about the same, 4 to 6%. It still has all those same parts that a normal combustion engine has. Okay, 4 to 6%. Auxiliary electrical losses, okay, 0 to 3%. There's more electrical stuff. Okay, you've got, if you have a regular hybrid, you have a driving battery, and then you have your gas engine. If you have a plug-in electric hybrid, you have 2 different sets of batteries. You have a hybrid battery, and you have the pure electric vehicle battery. Okay, so there's going to be losses from those as current flows to the electric motors. Okay, drivetrain losses, 3 to 5%. Okay, when we're looking at drivetrain losses, 3 to 5%. It's still spinning wheels, it still has a transmission, all of that stuff's still the same. Okay, energy to the wheels is 24 to 38%. Well, why is it so much better than this one? Because when it runs on electric, it runs more efficiently. So it doesn't have to use as much fuel to do the same job because it's going to use electricity to do the job, okay, instead. And you can also do this, regenerative braking. This is like the game I play when I'm in our hybrid car. It's got a little coach, okay, and it tells me if I brake well, how much of the braking energy went back to the battery. Remember we talked about the first day how hybrid vehicles have that thing in the brakes that turns the heat into electricity, goes back to the battery? I play a game with that. Okay? If I get 100%, I win. Okay? So if I brake efficiently, it tells me 100% energy return. So whatever energy I had, 100% of it went back to the battery. I'm sure it's not 100%, but it tells me that. Okay? And then I feel good about myself. Okay? If I have to slam on the brakes really hard, it tells me it's like 30%, and then I feel shame. So regenerative braking puts some of that energy that would have normally just have been turned into heat and vented to the outside into electricity. It goes back and charges the battery. It's basically free. Okay, my car didn't have to charge the battery because in a hybrid car, the gasoline engine is what charges the battery. In a plug-in hybrid, the gasoline engine charges the hybrid battery, but you can plug the other battery in from their house. Okay, so you got options there, but that energy still comes from fuel. The benefit is that an electric motor converts its electricity into mechanical energy at about 95% efficiency. A gasoline engine converts thermal energy to mechanical energy at 20% efficiency. Okay, so that's where your gain is in using that electric motor to be more efficient and save fuel. Okay, now, does that mean everybody should go out and buy a hybrid car? Okay, nothing comes for free. Okay, it's a matter of pick your poison. Okay, obviously we know the detractors for gasoline internal combustion engines. They produce greenhouse gases. Okay, they cause climate change, all that kind of stuff. Yeah, okay, we know that. Okay, but are there problems with having an electric car? Are there environmental impacts for an electric car? A lot. You ever seen a lithium mine? Okay. They make the oil sands look like a green, beautiful oasis. Okay. A lithium mine is a giant hole in the ground. Okay. And that's what goes into the batteries for an electric car. Okay. What happens to the batteries when they die? Because they don't last forever. Where do they go?
The ocean.
Well, hopefully not the ocean, but they go to landfill. Right? They got to go somewhere. I mean, we can say, oh, sure, they get recycled, but not all parts of them do. Okay? So there's going to be an environmental impact coming up here that people may not realize the disposal of all these electric car batteries. They have chemicals in them. Those chemicals are nasty. Okay? And they've got to go somewhere. All right? So yeah, there's things to consider. And here's the other part, at least in Alberta. if I plug my car in at home and I charge the battery, where did the electricity come from? Okay, where did it get, how did it get to my house? What did we use to generate it? Coal, burn coal. Yeah. Still most of Alberta's electricity is coal. Okay, we burn coal and then we make electricity from that. So, am I saving the environment? Not as much as I probably am told I am. Okay? I am still saving the environment because that electric motor is gonna use less energy to do the same job than the gas motor. So in that way, yes, I'm doing my part, okay? But you gotta consider everything. I'm saying there's no right or wrong answer here. You make a choice that fits for you, okay? But make sure you know all the sides of it, okay? A lot of people say, well, I'm getting an electric car because I'm gonna save the world, I'm gonna save the environment. You're gonna produce a lot less greenhouse gases, absolutely. But there's that, pick your poison. What happens to the batteries? The batteries maybe last 8, 9 years. I got a 10-year warranty on our car because I didn't want any part of having to replace them. Okay, so yeah, they're not going to last forever, and there's chemicals in them. And those chemicals have to go somewhere. Okay, electricity in Alberta is produced by the combustion of fossil fuels, so maybe I'm not saving the environment unless I've got a solar panel in the backyard that I can plug directly into my car. Okay, then yeah. Then maybe I'm doing a little better. Anyone got solar panels in their house? Yeah. Okay. Like I know there's a few people in my neighborhood that got them. Okay, and then certainly if I have an electric car and I got solar panels on my roof, I am doing more of my part to reduce the amount of greenhouse gas that I'm putting in. Okay, but the solar panels don't last forever either. They eventually go to landfill. They got nasty stuff in them too. Okay, so do your part, but do your research. Make sure you understand totally what you're doing when you make those choices. For me, I was like, free gas. I made the most selfish choice when we bought that plug-in hybrid car. Totally selfish choice. I'm gonna get free gas for as long as free gas is available. Okay, I'm sure eventually it's going to stop. Right. But for now, yeah. Is that making some sense? Okay, so that's a hybrid vehicle. Okay, the hybrid vehicle is quite a bit more efficient, energy to wheels. Okay, its lowest efficiency is almost the highest efficiency for just a gasoline-powered car. Oh, where'd the electric one? Oh, there's the electric one. Okay, if we look at a pure electric vehicle, okay, energy to the wheels, 87 to 91%. Okay, way more efficient. Converting electricity to mechanical energy is way more efficient. Okay? It's why, like, nuclear submarines work. Okay? They use electricity. All the motors that power them are electric. Okay? The nuclear power makes electricity, which turns the rotors. Okay? Instead of using diesel, okay, to turn the rotors. It's way more efficient. It's also quieter, which with submarines is important, I guess. Okay? So if we're looking at energy lost in charging the battery, 10%. I can tell you definitely when you're charging the battery, you're losing some energy. Okay? Mine makes this weird noise because there's a pump that circulates coolant around the battery because the battery gets hot while it's charging. Okay? Accessory losses. Accessories are accessories. That's your stereo, your touch screen, all of that stuff. Okay? Electric drive system losses, 18%. So we're still losing some. It's not perfect. Okay? Auxiliary electrical losses, 0 to 4, same as the other cars. Okay? Net regenerative braking, 22%. So I lose 18, but I can get 22 of it back by having regenerative braking, recharging my battery. That's pretty sweet. Okay? Idle losses. Well, yeah, they better be near 0 because what does an electric car do when it's idling? Nothing. Okay? There's nothing, like if you're in a gas car and you're at the stoplight and the engine's still running, it's still burning gas, it's still doing all that stuff. When you stop it at a stoplight in an electric car, it just sits there. It doesn't need any power until you press on the gas. So that way it's also more efficient. So you can still have all your stuff on in the line at Starbucks in your electric car versus if you're in a gas car. Okay. All right, is that making some sense? Okay, so we want to get as much out of the energy that we're putting in as we can. That makes us more efficient. Okay, so that's basically the definition of efficiency. Okay, so our initial energy source is EI, our energy input. Okay,
The desired energy is our energy output, which we call work, the work that the object, machine, whatever will do, okay? And then the work that the machine is supposed to do is the useful work, okay? Okay, so like we were talking about, systems with moving parts are always going to lose energy as heat because there's always going to be friction, drag, all of that kind of stuff. Okay, so energy supplied to your body by food, okay, has to equal all the useful work done plus all the wasted energy, which includes heat and mechanical energy of the parts of your body. So even you as a machine are not 100% efficient. Okay, your body as a machine is not 100% efficient. Okay, that's why we sweat. And if we work hard, we produce a lot of extra heat that we don't need, and we have to cool our bodies so we don't get overheated. Okay, so if we're looking at efficiency in terms of calculations, this is what we do. Okay, to calculate our efficiency, okay, we take the useful work that the machine does, okay, the useful work output, and we divide it by the total work input. So this would be, if I was talking about my car or my truck, this would be the energy in my fuel. This would be what my truck actually does. Okay, so I divide that number by that number and then multiply by 100. Okay, and you don't even really have to do that because you can do that in your head, right? When you calculate your score on a test, your percentage on a test, you probably don't multiply it by 100. You just go, oh, I got 0.85. I got 85%, and done. Okay, everyone all right with that? Okay, so that's all that efficiency is calculated as. It's calculated as a percentage. Okay, so let's look at this example here. So if I've got a crane and it lifts a load of construction materials, whoa. That's not good. Messing with me. All right, so a crane lifts a load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.3 times 10 to the 4 joules of work or mechanical energy input. So that's how much energy it uses, okay? While doing 8.0 times 10 to the 3 joules of useful work. Okay. How can I always tell the difference if the wording is weird? How can I tell which one is which if the wording is misleading? It kind of is here. Which number is always going to be smaller? Well, the efficiency is going to be the percentage I get, right? So I got a number on the top, I got a number on the bottom, okay? Useful work goes on the top, energy input goes on the bottom. Which one's always going to be the smaller number? Other way, output, okay? Because no conversion is 100% efficient, right? That means the number on the top has always got to be smaller than the number on the bottom, okay? The number on the bottom is how much energy I had to put in. The number on the top is how much work actually got done, and that number is never the same as the energy I had to put in to do it, right? So the number on the top is always going to be the smaller number. Otherwise, you'll get something that's more than 100% efficient. If you ever do one of these calculations and you get 1 point something for your answer, you did something wrong. Or you discovered the greatest thing in human history. So probably something wrong, okay? Because it would violate the laws of thermodynamics for you to have something that was more than 100% efficient, okay? Because it means you're creating what? You're creating energy. That goes against the first law of thermodynamics, okay? So if you ever get a number that's greater than 1, you probably just got the numbers reversed. Okay, so my energy input in this question is 2.3 times 10 to the 4. That's 23,000 joules. Okay, the useful work, that would be the mechanical energy output, is only 8,000 joules. Okay, I want to calculate the efficiency of the crane. All right, so efficiency is the percentage, okay, and it's EM over EI. That's 8,000. Divided by 23,000, right? and that's gonna give me 35%, 34.8% efficiency.
Okay. So this formula is not hard to use. It's the same, like I say, the same formula you use to calculate what percentage you got on a test. Okay? You take what you got out of, divided by what the test was out of. Okay? Same idea.
Anyone need that anymore? Computer is really laggy today. All right, I would like you guys to try the first 3 problems here. So they're all using this formula, okay? So percent efficiency equals EM over EI. So some of them are gonna ask you to manipulate this equation. Is this a hard equation to manipulate? No, you just have to remember that whatever the percentage is, you need to put it into here as a decimal. Okay, so 15% in this formula is 0.15. Right, that's the only thing you have to do. Okay, the only kind of weird thing. Then manipulate for what you don't have. Give you a few minutes, and then we'll go through number 1. So as with any problem-solving question we've done in this course, mole equation, any of the stuff in the physics unit, okay, what's the first thing I want to do? Write down my givens, yeah. Okay, so in this one here, I know the efficiency, okay, is 0.15, right? It's used to do 3.2 times 10 to the 4 joules of useful work. Okay, useful work is the top number, right? So that is EM, right? So we are looking at 3.20 times 10 to the 4 joules. It's the useful work part, okay? Always look for those words, useful work, okay? That's the top number. Okay, energy input or energy used, that's the bottom number. Okay, so what I'm looking for then is the bottom number in this one. Right, so I gotta take this formula and I gotta solve for EI. Right, so that means I'm gonna multiply both sides by EI, and then I'm gonna divide both sides by efficiency. So when I plug in my numbers then, that's going to be 32,000. Okay, that's 3.2 times 10 to the 4, okay, divided by 0.15. And if I do that, I should get 213,333.33 joules worth of energy input. Right? If something's running at 15%, I got to put in a lot more energy than the work I actually got out of it. Would you agree? That's why that number is so much bigger than the useful work number. All right, give you a little more time here on 2 and 3. Okay, so number 2 is pretty easy because it just wants the efficiency. We don't have to do any manipulating on number 2. Okay, we're told that the mechanical energy input, that's the bottom number, 5.61 times 10 to the 4, or 56,100 joules. Okay, that's our energy input. Our mechanical energy output, or useful work, is 19,600 joules. Okay, calculate the percent efficiency. Okay, well, efficiency then is going to be 19,600 joules divided by 56,100 joules, okay, and that should give us 34.93%.
Would you lose marks if you round to 35?
Nope,
Okay.
you wouldn't. In fact, I think on the test, I don't even have any decimal places on the answer. I'm sure it did have decimal places, but I didn't. All right, how many people have done number 3? Okay, let's look at that one too then. All right, so small electric motor has an efficiency of 85%. So efficiency is 0.85. Okay, in lifting a small load, it produces 15 joules of mechanical energy input. That's the bottom number, 15 joules. Okay, calculate the useful mechanical energy output of the motor. That's EM, that's the top number. All right, so efficiency equals EM over EI. To get EM by itself, what do I do with EI?
Multiply.
Multiply it over to the other side. Okay, so that's gonna mean, 15 times 0.85, that's gonna get us our 12.75 joules. Okay, making sense? Okay, not too tough to use, right? And that formula is on your formula sheet. Okay, so it's not like you have to memorize it or anything. It is on there. Okay, did I talk to you guys about finals and stuff yesterday? Okay, I think so. All right, just 3 weeks left. Yeah, there was just 3 weeks yesterday of class left. Okay, you have obviously a couple more lessons in this unit. Okay, we're doing a unit exam review on Monday. We're doing our lab on Tuesday. Your test is Wednesday. All right, we'll go over the test on Thursday and start unit 4 on Thursday. Okay, and then we'll have about 8 or 9 days to do it, which is lots. Okay, so once we're done the unit exam for this unit, I will put the date up for the unit exam for the last unit. Okay, so that you can start planning around that last week, because that last week gets pretty crazy, right? That's when term papers have to come in, okay, when you got exams in every class, right, all that kind of stuff. So I want you to be able to kind of plan things going forward. Your final exam, okay, for this class obviously is the 20th, okay, it's in the morning. So my suggestion is this. You want to spread your studying out as much as possible. Because if you're looking at your exam schedule, maybe you've got another exam that same day, okay, things like that, and you're going to start to feel overwhelmed if you leave it till the last minute. Plus, cramming is not an effective way to study. Okay, if your plan was, I'm just going to pull an all-nighter and throw in 10 hours the night before, that's really a bad idea. Okay, you definitely don't want to do that. Because here's what could happen. You're at hour 7, it's 4 o'clock in the morning, and you're like, uh-oh, I don't remember how to do mole equations. I'm not getting any of these right. If you email me at 4 in the morning, Mr. Coderre, how do I do mole equation questions? You will be met with silence, because I will not answer, okay? And you will not find me the next morning, because I will hide, okay? Actually, I won't hide. I'll be putting up my exams. I have to do that morning. You won't see me, and you won't be able to get help because you left it till the last minute, okay? So, here's a better plan, and it's not gonna feel like as much work. If you go home each night and spend 5, maybe even 10 minutes looking at your science stuff, that'll add up over the last 3.5 weeks. I say half because you got that extra few days there between the end of classes and your exam. Okay, it'll add up in a big way. So if you go home, let's say tonight, and you try a couple of reactions. Okay, go back in your digital workbook and see if you can still predict the products of a reaction and balance it. Just try a couple, take you 5 or 10 minutes, right? And if you get them all right, because you can check them, because you have keys for that on Google Classroom as well, you'll go, all right, I still remember how to do chemistry. Okay, that's good, now I feel a little better about everything. Okay, and then the next night you go home and you go over the diagram of the cell. Okay, see what you remember from that. But if you pick away at it in really small chunks, not only will you commit it to memory a lot better, but it won't seem like as much work. Okay, and then the night before, when you're doing your final review, you'll be going through stuff. I know how to do that. 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 And you won't have to do as much. And you'll probably feel a lot less anxious about all of it because you'll know you already know how to do it. And if there is something you don't know how to do, you can come in and see me because you did it 2 weeks ahead of time. Okay? And you can pop in at nighttime or whatever and ask me questions. So that would be my suggestion for you in terms of final exam prep. Don't wait. Don't put it off, okay? Manage your time.
Will the final exam go by the or will they all just be mixed?
It is very much sectioned. Yeah, so there'll be a bunch of multiple choice on chemistry, a bunch of multiple choice on bio, so it's very sectioned, and then the written goes the same way.
Okay.
And it's the exact same format as a unit exam. It's multiple choice, and then there's written responses. Just like a unit exam, except longer. Okay, because you got longer to write. For your exam next week, okay, I will let you guys start during lunch hour, okay, so you can write to nighttime, right? So if you come in at about, let's say, 10 to 12, okay, on Wednesday of next week, I'll let you get started. That'll get you an extra 20 minutes or so to write, okay? So you can have that. And then, because I'll have to let my other class start during that time, but I'll probably let you cross over a little bit if you need to.
If you normally write in learning support, the test's there already, you just have to go and get it from them. I've put the formulas on the front page of the exam, so don't bring your periodic table / formula sheet, okay? The formulas are all on the front of the exam instead. And make sure you have a real calculator. You cannot use your phone as a calculator on a unit exam because your phone will be in the little blue box at the front, okay? So beg, borrow, or creatively acquire a calculator before next Wednesday. I only have a few to lend out, and if you're the last person and I've run up, you're really up the creek. Okay, so, I don't want that for you. Alright, questions on that stuff? Okay, we will do obviously some final exam review, we'll have time for that. Okay, so we'll do a little bit of final exam review in class, but probably not a ton. Okay, but we will have a little bit of time, so make sure you got questions ready for that last part. Okay. Alright, that's all I got for you.